Hey, hello everyone. Today we'll be learning about subtopic 3.2 wave particle duality. Okay, before we begin, let me give you a scenario. Let's take, for instance, right, there's a very large globe. On the left-hand side of the globe, it is blue in color, and on the right-hand side of the globe is red. And there are two groups of people. One located on the left-hand side, they claim that the globe is blue, and the group that lies on the right-hand side who claims that the globe is red. And they're trying to convince each other that what they see is correct. Okay, that was what happened to light. When scientists studied about light, there was two groups of scientists. One group believed that light was a wave, and another group of scientists believed that light was actually a particle. So the group that believed that light was a wave was like Huygens, Thomas Young, and the group of scientists that believed that light was actually a particle was actually Newton and everyone else, due to the fact of Newton's reputation, right? Every other scientist also believed that light was actually a particle. But like all good scientists, if you believe that a certain theory, right, you have to come up with experimental evidence to prove that your theory is right. So experiments to show that light behaves as a wave was actually carried out by Thomas Young in his famous Young's double slit experiment. So there's no other way to explain why light experiences constructive and destructive indifference unless we look at light as a wave, where a crest from one wave meets up with a crest from a different wave to give you constructive indifference. Diffraction of light. So there's no other way to explain why light diffract unless if we consider that light is actually a wave. On the other hand, to show that light was actually a particle, there was unfortunately, right, there were no experiments at that time. So the theory of light as a particle eventually faded away. So for a few hundred years, right, the theory that light was actually a wave was the dominant theory until the Hertz experiment. Okay, what is this Hertz experiment? So Hertz experiment, all right, was carried out using two electrodes, all right, one positive, the other one is negative. And Hertz exposed this negative electrode to colored light. So initially he used red light and nothing happened. Then he changed the frequency to higher and higher frequency. But to his surprise, when he used blue light or violet light, he observed sparks moving from the negative to the positive. So when he used low frequency light, nothing happened. So when he increased the intensity of this low frequency light, nothing happened. It was only when he used violet light that he saw sparks moving across. So that experiment could not be explained by using the concept of light as a wave. So now we know that light is actually a wave as well as a particle. So it all depends on which experiments that we carry out to show. If we carry out an experiment to show that light is a wave, then light would show wave-like behavior. Okay, so light basically are particles, and these particles are called photons. And these photons have energy E equals to hf. H is your Planck's constant, and F refers to the frequency of the light. And light again has momentum, and the momentum of photon is given as h divided by lambda. H again is your Planck's constant, and lambda is the wavelength of the light. Okay, so in our syllabus, we don't need to derive or to prove this relationship, right? So what is required in our syllabus will be basically knowing that the energy of photon is hf and the momentum of photon is just h over lambda. So subsequently calculate the energy of a momentum and photon in various regions of your electromagnetic spectrum. Okay, so this is Planck's constant. It's given in your formula sheet. Okay, so let's try this example. Pause the video for 3 minutes. And once you're ready, resume this recording. Okay, in this example one, calculate the energy of a photon of frequency 1800 megahertz. And B, right? Determine the number of photons arriving per second if the total energy is 0.60 joules, given your Planck's constant. Okay, to calculate the energy of a photon, we use the formula E equals to HF. So the frequency is given as 1800 megahertz. So change it to joules, right? So change it to SI units, all right? So the SI units for frequency will be in hertz. So energy is HF. So Planck's constant times the frequency, which is in hertz, will give us the energy in terms of joules, 1.19 times 10 negative 24 joules of energy. Okay, for B, right? So how many photons will be arriving per second if the total energy is 0.60 joules? So for B, right, the total energy, which is 0.60 joules, and this is the energy of one photon. So the question is, how many photons do I need of this energy arriving per second to give me 0.6 joules of energy? So energy of one photon will be 1.19 times 10 negative 24 joules. So substituting in this formula, right, we can find N. So N here will be 5.03 times 10 to the power 23 photons. So you need this total number of photons arriving every second in order for the energy to be 0.60 joules, all right, per second. Okay, this frequency, right, is basically the frequency of your mobile phone, 1800 megahertz. So if we consider mobile phones, whenever we talk on a mobile phone, right, we are using typically about 0.60 joules of energy. So imagine the amount of photons that we use per second to communicate will be 5.03 times 10 to the power 23 photons. Okay, let's try exercise 2. Pause this video, all right? Okay, in this example, an electron with initial kinetic energy 1.2 times 10 negative 17 joules of energy, right, enters two parallel plates. So these are the two parallel plates and strike point A. So the electron comes in with 1.2 times 10 negative 17 joules of energy is coming through here and it's moving towards point A. Take note, point A is the negative plate. The electron is negative, so it's moving towards a negative plate. So in part A, right, find the final kinetic energy of the electron at point A. Okay, to solve this, all right, the hint here we use energy in terms of electron volts and using the law of conservation of energy. So remember, energy can be represented in terms of electron volts. It is just a convenient way of representing energy. However, electron volts is not your SI, MKS units of energy. So using the law of conservation of energy, and what's the law of conservation of energy, right? Basically, total initial energy or the total initial kinetic energy of the electron will be 1.2 times 10 negative 17 joules of energy. So what we do is we convert the energy in joules in terms of electron volts. So in other words, the electron is coming in with 75 electron volts of kinetic energy. So using the law of conservation of energy, so the law of conservation of energy states that the total initial energy is equals to the total final energy. So the total initial energy is made of potential energy initial and kinetic energy initial. And the total final energy is made of potential energy final plus kinetic energy final. Okay, initial potential energy, which is this part, right, is actually 0. Okay, it's easy to find out whether there's potential energy or not. So in this case, when the electron is moving across this region, right, is it moving across a potential difference? The potential difference will be something like that, measured in terms of volts. So when the electron is moving in this region, is it moving across a potential difference? The answer is no. So therefore, initial potential energy of the electron is 0. Initial kinetic energy is 75 electron volts. Okay, final will be this region, right? Once it enters the 2-para plate. Potential energy final. Yes, there is potential energy final because it's moving across a 50-volt potential. Okay. So in this case, if we represent energy in terms of electron volts, when the electron, right, that is moving across a potential of 50 volts, there'll be work done. And the work done is equals to Q delta V. Q is the charge of electron times the potential difference that is 50 volts. So we know the electron has initial kinetic energy of 75 electron volts. The final is made of potential energy as well as kinetic energy. So from here, we can find the kinetic energy of the electron, which is given as 25 electron volts. So let's describe what happens. The electron comes in with 75 electron volts. Now it moves across a potential of 50 volts. So as it moves towards the negative plate, right, the potential energy of the electron increases by how much? By 50 electron volts. So at the same time as the potential energy of the electron increases, its kinetic energy reduces because the total final energy or total sum of energy must always be conserved, right? That means if potential energy increases, then kinetic energy has to reduce. So that's why the kinetic energy final has reduced to 25 electron volts. Okay, try to understand this concept because this concept is important, right? Later on when we learn about photoelectric experiment. So once you've got our answer in terms of electron volts, we can convert our energy back to joules, which is your SI MKS units of energy. Okay. Now, pause the video again and try to answer part B. So the question in part B will be, what's the potential needed to stop the electron at point A? Okay, to answer this, come back to question 2A, right? What's the kinetic energy final of the electron at point A? So in this case, right, just to recap what happened in question A, the electron comes in with 75 electron volts of kinetic energy. It moves to a potential of 50 volts. That means it gains 50 electron volts of potential energy. So at the same time, when it gains 50 electron volts of potential energy, it loses kinetic energy. So therefore, by the time it strikes point A, the kinetic energy final is given as 25 electron volts, right? From 75 here, when it strikes point A, it has a balance of 25 electron volts, which is equivalent to 4 times 10 negative 18 joules of energy. So in part B, right, what's the potential that's required to stop the electron? That means what is this value? So that the electron loses all its kinetic energy and it stops at point A. So to answer this, again, we use the law of conservation of energy. initial energy at this point is 0 because the electron doesn't move across any potential difference. But it has 75 electron volts of kinetic energy. At this point, final point, which is point A, now the electron stops. So the final kinetic energy of the electron is 0. So in this case, the initial kinetic energy equals to the potential energy that the electron gains as it moves from the negative to the from the positive plate to the negative plate. So in this case, kinetic energy is 75 electron volts, and the potential energy, which is equivalent to the work done, is given as E delta V. So cancelling off common factors E, we can find that the potential will be 75 volts. So in other words, if I change the potential from 50 volts now to 75 volts, you find that the electron will stop at point A. So this potential is known as the stopping potential. All right. So take note, stopping potential is the potential required to stop the electron. Okay, without calculating, what is the kinetic energy final at point A? The potential is 75 volts. 1 minute. All right, so what's the kinetic energy final at point A? Take note, what I've done is I've changed the potential. Now this is negative and this is positive. So when the electron is coming in with 75 electron volts of kinetic energy, the moment it enters the two paraplates, the electron that is negative will say, oh, this is positive. So what's going to happen will be, it's going to gain kinetic energy. So when it gains kinetic energy, it's at the expense of the potential energy. So potential energy has to reduce so that the kinetic energy increases. So how much energy would the kinetic energy increase? So since I apply this to be 75 volts, the electron is going to gain another 75 electron volts of kinetic energy. So by the time it strikes point A, it will have 150 electron volts. Okay, why 150? Because initially it has 75. When it moves across a potential of 75, it again gains 75 electron volts. So 75 times 2, that's why you get 150 electron volts. So be very careful. Look at what's the polarity of this plate. In A and B, this plate was negative, and this plate was positive. In C, right, now I've changed the potential. This becomes negative, and this becomes positive. Okay, if you're wondering, right, when the electron is traveling here, the electron that's negative, wouldn't it be repelled by this negative plate? The answer is no. Because remember when we learned about electric field for paraplates, anywhere inside the paraplates, there'll be uniform electric field. Outside the paraplates, the electric field is 0. So when the electron is approaching this negative plate, all right, when it's approaching here, the electric field is 0. So if the electric field is 0, the force that acts on this electron is 0. So the electron will be moving, right, with constant kinetic energy. The moment it enters the paraplate, that's where it experiences uniform electric field created by these two paraplates. And at this region, it experiences a force, which slows it down, which causes the kinetic energy to change depending on whether the electron is moving towards a negative plate or whether it's moving towards a positive plate. Okay, let's try another example. Pause this video. Okay, in this question, right, the diagram below shows an electron gun. So this is electron gun. So electrons are emitted from the filament here by thermionic emission and accelerated through a potential of 320 volts. So you're given the mass and charge of an electron. So in A, right, determine the kinetic energy of the electron emitted from the electron gun. So determine your energy in terms of electron volts. And B, determine how fast electrons will be moving once the electron comes out from this electron gun. Okay, so basically, right, from here, we know that this terminal is positive. So the electrons, all right, that are negative will be accelerated towards this positive plate. And when they come out, they are going to come out with very high kinetic energy. So let's again use the law of conservation of energy. So law of conservation of energy says that the total initial energy must be the same as the total final energy. So total initial energy will be made up of potential and kinetic. Okay, let's look at the initial state. This is your initial state. Is there potential energy? So it's easy to identify, is there potential energy? Electrons here, are they moving across a potential difference? Are they moving across a battery? Yes, they are. So in this case, there'll be initial potential energy. Is there initial kinetic energy? The answer is no. So although the electrons are emitted by a thermionic emission, right, the electrons will have negligible amount of kinetic energy. So we say that the initial kinetic energy of the electron is zero because there is thermal energy. So thermal energy will be 0 point something electron volts of kinetic energy. So we can just ignore it. Okay, total final energy, again, is made up of potential as well as kinetic. So is that potential energy final? So when the electron comes out, all right, at this region is your final condition. Is it moving across a potential difference? The answer is no. So potential energy final is actually zero. Is the electron having final kinetic energy? Yes, they are. So the electrons are going to come out with very high kinetic energy. So from the law of conservation of energy, the initial potential energy equals to kinetic energy final. And the initial potential energy is equals to the work done on the electron. So work done on the electron is just given as Q delta V. Q will be the charge of the electron. Delta V will be the potential, accelerating potential, which is 320 volts. And from here, we can equate this to kinetic energy final. So equating this, we can know kinetic energy final will be 320 electron volts. So you see, when we learn subtopic 2, right, 2.1, 2.2, when we learn about electron volts of energy, we found that electron volts is just a convenient way of representing an energy. Because if I apply this to be 500 volts, then when the electron comes out, they are going to come out with 500 electron volts. This is 320 volts. So the electron comes out with 320 electron volts of kinetic energy. Okay, for part B, how do you find the final speed of the electron from the kinetic energy? Okay, to find the speed, we use kinetic energy, which is half mv squared. So we know we are given mass of electron, we can find V because we know the energy. However, be very careful, 320 electron volts is not your SI MKS units of energy. So we need to convert electron volts to joules. And how do we do that? We times the conversion factor. So the conversion factor will be 1 electron volts represent 1.6 times 10 negative 19 joules of energy. So that's how we convert electron volts to joules. And then we can use this formula to find V. So solving for this, we can find, okay, the final speed of electron when it comes out will be 1.0 times 10 power 7 meters per second. Okay, let's try this example. Okay, atom X has one valence electron orbiting at 8.2 times 10 negative 12 meters away from nucleus X. So this is your nucleus, and this nucleus has 2 protons. So in A, right, find the acceleration of the electron about the nucleus. So the hint here will be use Coulomb's law and Newton's second law. Okay, Coulomb's law is given as the electrostatic force that exists between the nucleus and the electron is given as K, Q1, Q2 over R squared. So Q1, let's consider the electron is Q1 and the nucleus is Q2, right? So Q1 will be the charge of electron and Q2 will be the charge of the nucleus. And equating this to Newton's second law, F equals to ma, we can find the acceleration that the electron is going to experience, right, when it is moving around the nucleus. Okay, so when we substitute all this, K, right, this is the value of K, 9 times 10 to the power of 9, divided by mass of the electron, charge of electron, charge of the nucleus, divided by their separation squared. Okay, the charge of the nucleus, right, since it's made of 2 protons, the charge of the proton is same as the charge of an electron. So that's why, since there are 2 protons, we just times the charge of a proton times 2. So solving for this, we can find the acceleration that the electron experiences is 7.52 times 10 to the power 24 meters per second squared. Okay. So the classical model, right, say that, okay, the electron is actually orbiting the nucleus, right? So in this case, what's the frequency and what's the wavelength of the photon emitted? Hint, all right, use uniform circular motion. Okay, in our previous part A, right, we have already found the acceleration of the electron. And in part B, right, the electron is actually orbiting the nucleus in a uniform circular motion, where the acceleration is given as v squared over r. So we have the acceleration, so we can find the frequency in which the electron is orbiting the nucleus. So v equals to 2 pi r over t. Remember this formula when we learned subtopic 1, mechanics. So frequency and period. So substituting into this formula, acceleration, which is 2 pi r frequency squared divided by r. So cancelling out common factors are r squared and r, and finding frequency, we can find the frequency to be 2.32 times 10 to the power 14 hertz squared. Or basically the frequency will be 1.52 times 10 to the power 17 hertz. Okay, so that's the frequency of the charged particle orbiting the nucleus. Okay, in topic 3.1, when we learn about electromagnetic radiation, we learned that any charged particle that vibrates, right, or has a certain frequency is going to emit electromagnetic radiation, where the electromagnetic radiation will have the same frequency of the charged particle. So in this case, right, when this electron moves in a circular motion, it has a certain fixed frequency. So in other words, it's going to emit electromagnetic radiation with a frequency that is the same as the frequency of the charged particle. So since we know the frequency of the charged particle, we can calculate the energy of the photon or the wavelength of the photon that's being emitted. So using this formula, lambda, we can find lambda, c divided by frequency. So from here, we can find the wavelength of the photon will be 1.97 times 10 negative 9 meters. So which part of the electromagnetic spectrum do you find this wavelength? This here actually lies in your soft X-ray region, right? So you see, right? Any charged particle that vibrates has a certain frequency of vibration. And from what we have learned in electromagnetic theory, since this charged particle moves in a circular motion, it has a certain frequency, so therefore it will emit electromagnetic radiation, which has the same frequency as the frequency of vibration of the electron. And this frequency, which is electromagnetic radiation, will have a certain wavelength. And this wavelength is classified under soft X-ray. So see, right, find the energy of the photon and what's the momentum of the photon. So in 3.2, we'll be learning about light or electromagnetic radiation that has energy and momentum. So what's the energy and momentum of this photon? So if we use this formula, energy is hf. H is your Planck's constant times the frequency. We can find the energy of the photon to be 1.01 times 10 to the power of negative 16 joules of energy. So if we put in electron volts, we divide by the conversion factor, that is 1.6 times 10 negative 19, to get our energy in terms of electron volts or in mega electron volts. So mega is times 10 to the power of 6. So the photon that's emitted is 0.631 mega electron volts. And what's the momentum of this photon? So momentum of photon is momentum is h over lambda. So since you're given lambda, you can find the momentum. 3.37 times 10 negative 25 kilogram per second. Meters per second, all right. Kilogram meters per second. Okay, so this year, Tarser said the amount of energy that's released, right, by this atom is very, very high. This here is in the region of sub X-rays, right? It's actually very, very high. Okay, so by calculating this concept, right, we know that this model of atom doesn't work because if electron is orbiting a nucleus, it's going to emit energy. So it's going to lose energy, and eventually is living cells will be constantly bombarded by this high energy radiation, and people will die. So it's not possible for atoms, all right, to constantly emit radiation. So this model is not right. So let's review through. So light in this chapter behave as particles, which we call as photons. And these particles will have energy, hf, and momentum, h over lambda. So in our syllabus, you need to calculate the energy and momentum. So if given frequency, calculate the energy. If given lambda, calculate momentum. Or basically, if I give you frequency, you can find lambda. And once you find lambda, you can calculate the momentum.